Hi everyone, so in this video I am going to prove the derivative of the inverse sine function, also known as the arcsine function. And in order to do that, we're going to need some things that we'll put all together in our proof. The first is we're going to need some information about inverse trig functions themselves and how those operate. We'll start there, and then we're going to look at this specific question where we simplify cosine of arcsine of x, and that's going to be very useful in our proof, the answer to that. And then we're going to look at what's called the Pythagorean identity, a very common thing to do in these trigonometric proofs. We're going to use implicit differentiation in order to work through and solve this. And then at the end, we'll do a list of the rules of all of the different derivatives of the arc trig functions, the inverse trig functions. So we're only going to prove the derivative right now for the inverse sine function, but then I'll show you at the end of the video all 6 of the inverse trig function rules, and each of the proofs for the other ones are similar to this first one. So here we go. So starting with some information about inverse trig functions themselves, it's important to really understand what they are and what they do. So one thing is that if you do the inverse sine of x, then you're going to get x back out. So you're basically doing sine of x first, and then you're undoing that sine function. So you get back the identity of what you started with. You get back x. Now in this one, the domain would have to be things that are going into the sine function, and we would need this to be a one-to-one function. So this only happens if x is in between negative pi over 2 and positive pi over 2. Okay, so we're just there in the middle of the graph when we're talking about that idea. The second thing that has to happen is if we switch these around and we do sine of inverse sine of x, then we'll also get to x. And it's the same idea that the sine and the inverse sine function have to undo each other, but in this one, notice the x values are going into the inverse sine function. So they would have to be fractions that are between 1 and negative 1. So this has to happen when x is in between 1 and negative 1. Now, the next thing we want to look at is how we can do a specific example of figuring out cosine of inverse sine. And that's something that we're going to use, along with just the general understanding of what it means for sine to be an inverse trig function, and to understand the domains of what we're talking about. We're going to get into a specific example that'll be very useful. So we want to simplify cosine of inverse sine of x. So here's how that's going to look. And we're going to need to take advantage of what we had on the previous page where we said sine of inverse sine of x is x. Okay, so we're going to use that. Now, in order to use that, we're going to need to start with what's called the Pythagorean identity. We're going to use the Pythagorean identity, sine squared y plus cosine squared of y is equal to 1. And then what we'll need to do is rearrange that identity a little bit to just get cosine squared y on the left. So we're going to get cosine squared y on the left. We're going to subtract sine squared y from both sides. Okay, so now if we let y equal the inverse sine of x, then we can substitute in to what we have and get cosine squared of the inverse sine of x has to be equal to 1 minus sine squared of the inverse sine of x. And the reason that we did this is we are looking to use our idea from the previous page. We're looking to use this idea right here. And you notice over at the end of our current equation, we have something very similar to that. It's just that we have the squared that's also in effect. So what we'd like to do next is take the square root of both sides of this equation. And when I take the square root of the left side, I'm going to get the absolute value of cosine of inverse sine of x. And you'll notice that is the absolute value of what we're looking for in this example. So right up here, we're looking for simplifying cosine of inverse sine of x. And down at the bottom, we currently have the absolute value of cosine of inverse sine of x. And on the right side, we'll have the square root of 1 minus. Now, what's going to happen here if we have sine squared of inverse sine of x, and we know that sine of sine inverse of x is equal to x, then really all we have right here is x squared. And the other interesting thing that happens in this equation is think about these absolute values for a second. Now, we said that the inverse sine function up here is only going to be in effect when these x values are between 1 and negative 1. And when we put values into cosine that are between 1 and negative 1, or I'm sorry, when we put values in that are between negative pi over 2 and positive pi over 2, notice that cosine is going to be positive in that full interval. So everywhere that we are thinking about inverse sine being operational, it's going to make the cosine expression down here positive. So these absolute value signs are currently not doing anything. And what that means is that we can write that cosine of inverse sine of x is equal to the square root of 1 minus x squared. And that is going to be a useful result as we go forward and look at proving the derivative of the inverse sine function. So now we are ready to do so. So we're going to use implicit differentiation on this proof. We want to start with y equals the inverse sine of x. But before we take the derivative, I'm just going to switch this around and call it x equals sine of y. And notice that that is the same equation as I have up above. It's just been rewritten as x equals sine of y. So now when we take the derivative of both sides of this equation, we'll have the derivative with respect to x of x is equal to the derivative with respect to x of sine of y, where y is a function of x that we have up here at the top. You see, y is a function of x. And so when we take this derivative on the right side, we're going to use the chain rule, and we will get cosine of y times the derivative of y, which is dy over dx. And on the left side, the derivative of x with respect to x is just going to be 1. So dividing by cosine y on both sides and rearranging this slightly, we'll get dy over dx is equal to 1 over cosine y. And remember, y was just the inverse sine of x up here, so we have 1 over the cosine of the inverse sine of x. And the bottom of that expression is exactly what we figured out in our specific example. So we have 1 over the square root of 1 minus x squared. And it turns out that we have found the derivative of the inverse sine function in this way. The derivative of y with respect to x means the derivative with respect to x of our inverse sine function. And we've shown that to be equal to 1 over the square root of 1 minus x squared. Now you might need to go through that multiple times to see the full logic of how that works. But each of the derivatives of the inverse trig functions are going to work out in a similar way. So here are a list of all of the rules for the different inverse trig functions. You might want to pause the video to write these down and keep these as a reference. As you're doing so, I would just like to point out there's an interesting correlation here between the functions and their co-function partners. Notice that each of the functions of arcsine, arctangent, and arcsecant are positive. They have these positive ones on the top. And each of the co-functions have a negative one on the top. It's actually the only difference between the two values. So that's interesting to consider. I hope that this video has helped you to understand the derivatives of the inverse trig functions, and specifically the inverse sine function that we focused on. If you need any help figuring out the rest of the inverse trig function proofs, or if you have any questions, you can leave me a comment.